This video lecture here for the synthesis and characterization of polystyrene, experiment 5 in the Spring 21 Material Science 410 course. Goals of this lab are to understand the synthesis of polystyrene using a controlled radical polymerization techniques, and the lab will explore conditions where we vary the polymerization time and monomer concentration and use aliquots as molecular weight is building to try to establish trends in that molecular weight versus reaction time. In doing so, we'll aim to characterize the polystyrene using nuclear magnetic resonance, NMR, which is a technique that can quantitatively evaluate the conversion of monomer to polymer in this lab. We'll use size exclusion chromatography, a technique that can determine the molecular weight dependent on how the large macromolecules elute through a sort of nanoporous packed column. We use infrared spectroscopy. This will allow us to determine any functional groups and the conversion of those functional groups, like alkenes, into hydrocarbon. And there's even differential scanning calorimetry, DSC, which is a useful technique for studying the energy in and energy out of a material, something that we can use to determine the glass transition temperature and melt point of polymers. So typically in day one, students would work in pairs on the synthesis and prepare GPC samples or size exclusion chromatography samples. Day two is where students would again work in pairs and acquire NMR, FTIR, and DSC data and begin their data analysis and interpretation. For this lab in the Spring 21 session, we're going to have students prepare a technical lab memo as an individual assignment. Okay, so to ready us for some of the details of controlled polymerization, we'll first make sure we're familiar with the basics of a couple of types of polymerization. It is known that there are step growth and polymerizations, or also called condensation polymerizations. And these typically result from the linkage of monomers into a larger macromolecule at the expense of eliminating a small molecule. Typically, this is H2O, although HCl or other small molecule derivatives are known as well. What we usually see here is, in order to have the reactivity to eliminate small molecules like listed, is that we tend to have heteroatoms, that is to say oxygen or nitrogen, in the backbone, as these are give us the required reactive groups, such as amines, alcohols, carboxylic acids, to form groups like esters or amides to build up our polymer by way of eliminating components of those functional groups that have those heteroatoms. A complement technique for growing polymers is called chain growth, also known as addition polymerization. This refers typically to polymers that are made by free radical polymerization, although cationic and anionic and even coordination catalyst polymerizations are also known and considered chain growth polymerization. Here, polymers and monomers tend to be very hydrocarbon rich and would only generally have heteroatoms above should some sort of higher function be desired in the ultimate polymer. So at the industrial level, typical polymers that result from chain growth or addition polymerization are things like polyvinyl chloride, PVC, Teflon, acrylics like plexiglass or PMMA, polypropylene, polystyrene, polyethylene are some examples. Okay, and clearly polystyrene is a topic for us for this lab. So, step growth polymerization, where we expect to eliminate a small molecule, is exemplified here. So here we have a generic diacid molecule. So notice that we have a carboxylic acid at the beginning and at the end of this molecule, and we explicitly recognize that in the name diacid. So this diacid is bridged by a simple CH2 in the middle of the molecule. We mix this, add this, react this with a complement molecule to favor polymer formation. The complement molecule here is a diamine. So like in the blue structure, we're going to see a beginning to the molecule and an end to the molecule with the same functional group, two amine groups on the same functional group. And in the middle, we have two CH2 groups as the bridge, and we'll refer to that as the ethylene bridge. It is well known by small molecule reactions and these polymerization examples that amines with carboxylic acids can form amide groups. So the amide group is listed here. It consists of an appendage to the left of the carbonyl, and then immediately that carbonyl is attached to a secondary amine in this case. Okay, so we see the NH instead of NH2. And then there's an appendage to the right of that amine. So here, by connecting an amine to a carboxylic acid, we can favor an amide forming reaction. We recognize how this happens by considering the loss of one hydrogen from the amine and the OH group from the carboxylic acid. And so to sort of highlight that, let's just circle that. This would represent the lost small molecule to make the first amide group. After we do that, a new molecule is originated. That molecule would be terminated with a carboxylic acid at the beginning. It would have an amide in the middle, and then it would be terminated at the end with another amine. So that molecule is still able to react and generate other amide functional groups for the linkages down the main chain of this polyamide. The color coding here in the monomers of the diacid and the diamine makes it easy to recognize that every repeat unit that we generate in this polymer contains the majority of the atom units that were in the monomers. So we see the blue fragment represents the two carbonyls with that bridging CH2 group, and then we see most of the amine structure, so that as the primary amine has become the secondary amine for the amide functional group, and we see that ethylene bridge in the middle, and that repeats again to another secondary amine for the amide as we go across to the next repeat unit. So here, both monomers are showing a lot of their structure and atoms in the repeat units, and we've only lost a very small portion of each molecule to make our amide groups, that is the water. Okay, as a consequence, no matter how long this reaction goes, no matter what molecular weight builds, there will always be reactive end groups on the chain. So that is, the end groups will remain reactive. We'll see an amine group at the end of the chain. We'll always see a carboxylic acid at the end of the chain. So further reactions will be possible. Only in rare kind of academic work have people been able to access cyclic polymers to eliminate these functional groups. But in general, that is not considered a dominant reaction in industrial level polymerizations or other work. So again, we can rely on the fact that the end groups will always remain reactive and capable of further polymerization. Now, to contrast that to chain growth polymerization, so this is where we see a lot of hydrocarbon type molecules. We're going to see alkenes as a dominant feature there for polymerization, and these are going to react sequentially. Okay, so we're going to see these monomers add one by one in sort of a one-dimensional linear fashion rather than adding at both ends of the chain. So here's an example where styrene monomer, like we will see in this lab, becomes the only repeating feature in the repeat unit. And you can see that the alkene functional group, the double bond, is eliminated as we make linkages to and from the leading and the sort of tail of this monomer. So in this regard, as we grow polymer, we'll because we add one at a time in a linear fashion, we're only going to see one end that's reactive, and this will grow unidirectionally in that one direction this way. We're showing here the identity of that reactive group. So notice that there is a single dot. This indicates a free radical. And this represents the reactivity, the site of reaction for addition of additional styrene monomer or other alkene monomers if present. Okay, quite a bit different. No small molecule has been eliminated. And we largely recognize the feature in the repeat unit as being the monomer only. All the atoms that were in the monomer are present in the repeat unit. Additional bonds to the leading head group and the leading tail group of the monomer are what bridge across our repeat unit brackets here. Okay, some further comparisons are here. Here's step growth versus chain growth polymerization characteristics. So recognizing that there are two reactive end groups, the step growth polymerization can be kind of cartooned to recognize that dimer formation, it might be an early reaction step in generating high polymer as we move down sort of the scale of the reaction. So here a diacid could add with a diamine to give us our first generic dimer, as we see here. Trimers can form, so we would take that dimer and we would react it with yet another monomer. And so here a trimer can form. Tetramer formation might follow. So here that trimer can add a monomer. So again, that could be, the trimer might consist of two amide groups in the center of this oligomeric molecule with a appropriate and still reactive beginning and end features. And then we would react that with a complement monomer like a diacid or a diamine to make our first tetramer. Likewise, two dimers can come together to give us a tetramer in that next example. And so hopefully the pattern here shows you that a lot of different reactions between tetramers and pentamers and unimers, dimers, can ultimately build molecular weight in a more uncontrolled fashion, given the random assortment of molecules as they build in the reaction vessel. Okay, at every linkage, every time these generic circle features are added to a chain, we expect to eliminate a small molecule again. Okay, contrasting this to what we see in chain growth polymerization, where we have that unidirectional polymerization and only one reactive end group. To show this, we modify the generic picture here to include something called an initiator, which would generate and have which would have a radical, and that reactivity has to be transferred to the end of the first monomer, again represented by this zero kind of feature in our drawing. So here we expect that our monomer is now activated, it's bonded to our initiator, and it has the reactivity in the form of a radical if we're doing radical chain polymerization. That same feature is needed again in the next reaction. Another styrene must add to the activated styrene from the initiator, and we'll now make our next extended styrene molecule here. Okay, so we have two styrenes connected to our initiator. That same molecule is needed for the next reaction. Two styrenes connected to the initiator plus a free styrene to now make a trimer of styrene with that initiator. That trimeric styrene with the initiator needs another styrene, and we can build our kind of tetrameric polystyrene, and so forth. So unidirectional, we always add styrene to the one end. There will never be an addition of a monomer at the I end of the polymer chain. Okay, contrasting some characteristics of chain and step growth polymerization. Here we'll just note some additional features. So monomer tends to be added to a growing chain with a reactive terminus in chain growth polymerization. So we saw that just before on the previous slide here. So we're talking about this category here. Mixture tends to consist of very high molecular weight polymer and unreacted monomers. Okay, and we generally have very few chains that are growing. So as we see in our diagram above, here before polymerization, all monomers. Very quickly we have a few long polymers during the reaction and a lot of monomers. There are no dimers, no trimers, no tetramers, simply the unidirectional growing chain and free monomers available for later reaction. And of course, as the reaction proceeds, that molecular weight can build and we extend the chain in this kind of microscopic view with the generic R representing monomers. So we see that monomer concentration is going to decrease steadily as the reaction time proceeds, and that we're going to see high molecular weight very early in the reaction. And overall, the average molecular weight won't change as the reaction proceeds, given that the average molecular weight does in fact account for the very, very low molecular weight monomer as well. Increased reaction time will increase the overall product yield. So as we tether more monomer to the growing unidirectional polymer chain, that would contribute to product yield. And molecular weight may not necessarily drift from the average, given that we still account for monomer in the reaction mixture. Okay, so that is to say molecular weight depends on the initiator to monomer concentration, not necessarily time. Okay, for step growth polymerization, we see some contrasting to those observations. So the reaction can occur immediately between any pair of molecules. So any pair of molecules could be unimers, dimers, trimers, trimers with trimers, dimers with dimers, dimers with octamers. Any pair of molecules can react because they have those reactive end groups at both ends of the molecule. The reaction mixture consists of oligomers of many different sizes. We saw that a few slides ago. And the statistical representation of that is possible with modeling for the reactivity, and we can predict how many dimers, how many trimers, how many octamers might be present at any given moment in the reaction. Monomers, therefore, tend to disappear early. So that is to say, all R groups quickly become dimeric or trimeric or higher oligomers very early in the reaction, in favor of low molecular weight oligomers, that is to say where the repeat unit in the pattern, in the genetic here, so N will be low, on the order of 10 typically. Okay, so that tends to agree and help us understand definition of oligomers. N is on the order of 10. So very early in the reaction, we'll see a molecule species up to a repeating unit of 10, so decamers at best. These oligomers will only steadily increase the size of the polymer molecular weight as the reaction time proceeds, and typically these reaction times have to go very, very long to build appreciable molecular weight that is competitive with chain growth polymerization, sometimes weeks of reaction time versus minutes or hours for the chain growth example. So, as said here, long reaction times are going to be needed to produce polymers with that high molecular weight if we're to make a competing step growth chain with the chain growth option. So with that, we can now discuss a little bit about commodity plastics. So most commodity plastics are what we experience in everyday life. So they're produced in high volume, they have to be low cost and yet be high performance so that they can serve as a decent product for their ultimate purpose without failure. These tend to be derived from those alkene monomers. So that is to say they will be made by chain growth polymerization typically. Most of them are non-biodegradable. And most can be recyclable, so that is they can be ground up or used as filler or remelted, remolded, re-thermo processed into another part. And so, for example, our polystyrene can be reprocessed. Polyvinyl chloride can be reprocessed. Polypropylene, polyethylene can all be reprocessed, given the one-dimensional covalent linkages down the chain. So these are not thermoset materials and can be repurposed with thermal molding. A lot of other chain growth options exist, and so as we move away from the commodity materials that we see sort of at the bottom of this pyramid chart, we get to more engineering or high performance polymers. We can see both chain growth options as well as step growth options as we move sort of up the table here in favor of more high-end applications. Generally, the high volume required is only seen in the commodity materials, and as we move up the chain, lower volume options are known, and the applications are higher end, so cost can be compromised a little there too. An example there is polyether ether ketone, PEEK, P-E-E-K. This is a step growth polymerization product, and we're going to see here a carbonyl bridging with these very stiff and planar aromatic groups, and adjusted for flexibility with an ether linkage here, shown twice in the repeat unit. Okay, so recycling commodity plastics is something you're well aware of. There is recycling labels that indicate sort of the ultimate number of cycles of recycling and lifetime of the material. And we also have indicators often in those symbols for the type of material, like polyethylene terephthalate, PET or PET. Vinyl chloride or vinyl is sort of listed there. Low density polyethylene, polystyrene, a material we'll study in this lab, are also indicated with those abbreviations. And here's some rough estimates here for some of the materials in question. So polystyrene, the material for our lab, is produced in the US at a scale of about 2 million tons per year. It affords things like our styrofoam, our disposable and hopefully recycled glassware for personal consumption of goods, and even petri dishes, and even old compact discs or other cases for materials. You can see that $2 million or 2 million tons per year productivity is on the scale of some of these others, but certainly polyvinyl chloride, polypropylene, high density polyethylene are produced in even larger scales than that. And so clearly responsible consumer use and recycling is needed of those, as well as the polystyrene. So on that note, to give you a bit of a picture on the recycling of commodity plastics, we have this diagram here, provided by the ACS. And here we see, virgin feedstock of polymer, and just how much of it is in a closed loop recycling situation. So of the 98 moving forward here, to produce the plastic that's intended for annual global production and consumption, we get a complement 2% from that closed loop recycling to give us the 100% of our needed material. The majority of that material ends up incinerated, ends up disposed of in the environment or in the landfill, and only 14% of it goes through what's called recycling, where the recycling process has losses and even downgraded product given the recycling condition, and so the material can't go back into its original intent. So that perfect closed loop recycling option is muted given challenges in the recycling area. Okay, so with that, we'll end this video and